Thank you very much for having us. Delighted to share our Amundsen journey over the last year. We're going to show you a sort of brief overview of our implementation and dive a little bit more into table lineage, which is something we've been working on more recently. So I'll give you a little bit of context, and then Judy will take you through the technical parts. So who are we? I'm Rob. I'm an Associate Technical Director in the data engineering teams. I work out of our London office, and Judy's joining me today. She's a Senior Data Engineer working out of our Barcelona office. So for those of you who aren't familiar with King, we are a mobile game developer. We make great games and have developed more than 200 titles. They are played and enjoyed all over the world. We've got 245 million monthly active users as of Q3 2021, which is reasonably considerable, slightly more than the population of the US. And we've been part of the wider Activision Blizzard group since February 2016, so we're kind of part of a larger sort of gaming organization. If you don't recognize us as King, you will probably recognize Candy Crush, which is one of our kind of 4 main global franchises, others being Pet Rescue, Farm Heroes, and Bubble Witch as well. We have around 2,000 employees, a good number of whom are data literate or who intend to become data literate in the coming months and years as we look to democratize data further at King. So a few other sort of stats around kind of Candy Crush. So Candy Crush was once again the top grossing franchise in the US, and is still kind of growing year on year. So it's still remains quite a solid player base. So what does that mean for our data at King? So just kind of a few numbers to just sort of set the scene a little. From there, we're ingesting around about 80 billion events per day. We use BigQuery as our data warehouse. So all of our data is ingested into BigQuery and everything sits in there, which is quite convenient for our Amundsen implementation. We have around about 10,000 data sets, which relates to a hideously obscene number of tables, most of which are completely useless to the average user. It gets a lot of usage every day, about 500,000 queries. Of course, not all ad hoc. A lot of these are programmatic, powering dashboards, powering analysis, etc. And we estimate we've got around about 400 active data users. And by active data users, we mean people running SQL on BigQuery, or people exploring data through data exploration tools, or using dashboards. So the data discovery problem. When you have a large amount of data, it does become very, very difficult to discover, particularly as the organization changes and evolves, people move around, tribal knowledge is lost, etc. The landscape becomes particularly difficult, particularly for new joiners. So we wanted to start to address this problem. It was an ask that was coming our way and had been for some time. So around about this time last year, or a little bit earlier last year, we started digging into this and trying to define the problem a little bit better. And we started off trying to understand the behavior of data users, what they do when they start an analysis, how do they find the data that they need. And the most helpful method of finding and understanding data was by asking someone, either in person or Slack, and that was kind of the most popular way by quite some margin. And whilst that's a nice thing, we don't want to stop people talking to each other. There's a lot of waste there, particularly when you end up going from person to person and often not actually arriving at an answer. So one of our initial goals was to sort of change this initial behavior, because if we want to enable data usage further at King, this kind of time kind of perpetuates, and we want to kind of nip that in the bud. So we also ascertained that around about 28% of our data users spend, our data users spend about 28% of their time finding and understanding the data. And this is a metric that we believe we can reduce. This particular question was inspired by some of the LIFT findings as well. And we found a pretty similar number. And then we've kind of looked at actually ranking the experience. So firstly, how do we rate the overall ease of data discovery at King? We sort of wound up in the middle, 5.3. And then for kind of having confidence in that data, when you find it, having a kind of score of 6.2, both of which we don't think are good enough for the time being. And these are numbers that we wanted to move. So we set out on a POC. We started this in Q3 last year, and we landed with Amundsen in the end. We landed with Amundsen for a number of reasons. One, we liked the way that it was platform agnostic. We're able to go out and fetch metadata. We're not tied into any particular way of defining our data or defining our data pipelines. Teams are free to do that themselves, and that works particularly well at King because there are a number of different kind of distributed data engineering teams across the place, and quite a lot of them have different methods. So trying to get every team aligned on one particular method, at least in one go, would be particularly difficult and probably set us up for failure here. So we did a POC, we ran some initial user feedback sessions, and then sort of December last year, we released an alpha version to early adopters, which were a kind of small group of about 15 sort of data scientists and data engineers out and about the business at King. We then set up a champions group, and I think this was kind of one of the core things for enabling usage and getting kind of champions out in the data engineering teams and the data owning teams adopting Amundsen, because we as a platform team can throw out the software, but really the value of Amundsen comes in when you start adding that metadata, those descriptions, all of that kind of enriching content, and that has to be done by those that own the data. So we formed this group primarily to align on the methods that we would use to kind of define this data and how we would ingest it. And then in March, we beta released to the entirety of the company. And we're now at the stage where we have a good level of metadata coverage, at least for our, what we consider our most important tables and data models. We're about to release table Lineage, which Judy will show you, and a few other kind of King specific features in the UI as well. So this is kind of on the horizon. And with that, I will pass over to Judy to take you through the implementation and Lineage.
Thanks, Rob. So yeah, in my part, I would like to show you what Amundsen looks like for us. So yeah, so this is the landing page for table. In the top bar just next to Airflow, you can see landing times icon, which basically takes the user to a separate service showing freshness of data. The plan is to integrate it as part of Amundsen and just show the times directly in the UI. On the left-hand side, just below description, we've got data points related to the table directly. So stuff like documentation, partition and cluster, columns, number of rows, table grain, which is basically a list of cardinality columns for that table, Slack channel. And just below owners, we've got the list of users. Upon suggestion from our users, we have decided to split them into human users and the list of programmatic users, aka service accounts. Now, just at the bottom, there is a section with commonly used with. So it's basically a list of tables that this table is frequently used with. similarly, it would also disabled the editing of these fields. We also show badges for our columns. At the moment, we've got cluster and partition badge to basically mark it as such. The data is blurred, but in the description, we also show the column grain if it's different from that of table grain. Next slide, please. Cool. So I just wanted to give you a little bit of an overview on how our data warehouse is structured. And the reason for that is because one, I think it's interesting. It's an interesting use case, and another is that it ties to how we implemented Lineage in a way. So at King, we use this design pattern whereby basically each data domain serves its own customer-facing project. So there's this central project that is the only project that is served in Amundsen for that given domain. It lists the final resources, the customer-facing resources, basically with all the data quality and stuff, and it contains only SQL views, and that's the project exposed to our customers. And our customers include analysts, data scientists, managers, etc. Now, those SQL views, they basically read from many internal projects. It's basically a project in which ETL queries run. It has lots of stuff that is mostly not really intended for customers: tables, staging table, internal tables, staging tables, and staging views. But also the actual main table that is the result of the pipeline. So the views in the central project, basically 85% of those views link to a singular table in the internal project. So it has table-like attributes, stuff like clusters, cluster fields, partition fields, etc. But since we scan only the central project, which contains views, if we were to use the default extractor, we would lose this table-related attributes because it's a view. So next slide, please. So what we've basically done is when we fetch table metadata, some of the stuff we fetch from the customer-facing view, things like table schema, description, column descriptions, and the rest, stuff specific to the table, such as partitions, cluster, row count, the table last updated, the partition values that we fetch from the internal table from the data owner's project. Now, what really made it possible to extract it in this way is BigQuery API, because it basically allows us to fetch find out what table the customer view refers to. So next slide, please. So in terms of gathering metadata, the key table metadata we fetch from BigQuery and the BigQuery API. Now, the metadata such as usage, the commonly used with feature I mentioned before, or table lineage, all of it we fetch from logs. It's basically like a history of all the jobs in the process and work, and that basically this kind of is all of the information that we extract programmatically. Now, what I also think worth mentioning is that some of the pieces of metadata we fetch is declarative. So as Rob mentioned, we have this group of Amundsen champions, which basically are data owners. And we've basically agreed that the information that we are enabled to fetch programmatically, like contacts, table grain, column grain, the links, the GitHub pipeline documentation, they're going to be declared in data catalog. Data catalog is a GCP service that allows you to store information about tables, and basically you can define any kind of attributes that you want. So yeah, this section is pretty much declarative, and yeah, it worked out quite well for us. Next slide, please. Yeah, so I'm going to go into a little bit more detail about table lineage, and yeah, just talk about status quo and initial challenges. So this, I think, now was our first serious effort at try at Lineage. There have been some previous attempts done locally by teams, and we had some learnings from those. One learning was that it would be basically that the pipelines are incredibly complex, and it would be inevitable to make some simplifications and to basically manage this complexity. In terms of collection of data lineage, so a common practice for many companies is collecting lineage from scheduler. So, for example, Airflow has some plugins or extensions that lets you fetch this data automatically. The problem at King is that our data teams use different schedulers. Some teams mostly do not have lineage metadata at hand. Some of them have it, but on pipeline level rather than table level. And in the end users are much more interested in table lineage rather than pipeline lineage. So it was clear that the collection of lineage had to be programmatic. We had to somehow gather it from somewhere. So what I guess became clear is that GCP logs were a good source of data for lineage, because majority of our jobs basically are limited to SQL statements processed in BigQuery. All of those are really stored in are sent to GCP logging service. Next slide, please. So this is what GCP log looks like. This is a log of a SQL job. As you can see, there is the actual code that was executed, but the SQL log on its own is, if you were to use that for extracting lineage, it's not very useful, because obviously you have to parse the SQL, understand what's the input output of that query. So where GCP comes in very handy is that it actually gives you the metadata about that statement. So it gives you the destination table, so where the data, where was the output of that query written to. And it also shows you referenced tables and referenced views. So all of the resources that were used in that query to produce that result. So with that, we basically just querying those logs, we were able to have the ideal output, which is basically a row with 2 columns, an origin of data and its destination. Next slide, please. So the first iteration of Lineage, once we implemented it, it looked like this for us. So especially for the tables that are heavily used in DL and have a lot of downstream dependencies, it looked quite crowded, and at times it was unreadable. So I just wanted to talk a little bit about how our lineage extractor works. So the first step in the lineage extractor is basically running SQL on top of the logs that I mentioned, getting downstream and upstream. And then there is part of the SQL statement also this queries something called information schema, which is basically metadata about SQL views. And that gives us the input and output for views. It tells us which views or tables the given SQL view references. So all that combined gives us like an initial list of upstream and downstream pairs. Now, what we do is basically write that to memory, and we feed it into a Python function. So this is where basically the structure of data warehouse kind of becomes relevant, because some of the data that is outputted from that query, some of the resources are actually internal resources that also exist in the customer-facing project. Some of the ETL teams basically, rather than referencing the resources in the customer-facing project, they reference the internal resources. So the part of this function is to basically map the internal references to the public ones. It's like basically using, one common language. And then the second part is the simplifications I mentioned before. It's basically removing staging tables. So rather than including staging tables inside of the lineage, we basically look at the public resources those staging tables use or are generated from. So we do some reductions in the graph, and we end up with a cleaner version of Lineage. So all that we feed this final list of pairs of upstream and downstream, we feed into Amundsen. Next slide, please.
Apologies, I'm trying to. We've got a bit of lag. There we go.
No worries. Okay, cool. So with all these simplifications that I described inside of the extractor, the table lineage still looked like that. So basically we had to make some decisions about how we want to simplify this. Next slide, please. So we found that including a complete model of lineage makes the visualization quite difficult to digest, and it clouds the key information it conveys, and obviously reduces the value to the end user. So we've realized that perhaps we are trying to show too much all at once, and perhaps there is a way to get rid of some of the noise. So we ended up narrowing down the scope by hiding links between dependencies, which is what caused a lot of noise. And in the end, what we've done is basically focus on just one single question: what direct and indirect resources generate and depend on this table? And basically we tell our users that when you look at graph lineage, this is a complete list of resources that this table depends on or it generates. But since there is no straightforward way to show everything at once, how they relate it, how all the children are related to each other, you basically have to go to the lineage graph of the node that you're interested in. Next slide, please. So once we've made that change, the graph started looking much easier on the eyes. We basically have this graph whereby every node really has just one parent. And in general, it looks a lot cleaner, and users are able to at least read the table names and see what's the depth of the node. Next slide, please. So we have not long ago we have conducted a few workshops with our users and have received some very useful feedback on it. Some of it we have implemented, and other not really yet. So the first suggestion from our users was to collapse nodes of depth greater than 1. So rather than throw everything at once at user, basically just give them the bare minimum and let them unfold or open the nodes as they see fit. Other bits was, other pieces of feedback was, for example, on the lineage graph was to show table location. When you have a really big data warehouse, it's possible that some of table names may be duplicated, or table names from two different domains may look very similar. So a possible suggestion would be to basically show that a tooltip for a given node and show the data set and project it comes from. Another piece of feedback was, since we have already simplified Lineage a little bit and hit some of the links, we were to allow clicking through from the node to that table, to the table page of interest. So that would make the user experience a little bit more smooth. Next piece of feedback was to improve scaling of Lineage graph, because when you have a lot of nodes loaded, especially with those very heavily used tables, it becomes a little bit crowded, and some names overlap and it's difficult to read. So it's still, even with all those customizations we made, it's still, there's some improvements in the area of scaling and displaying it differently. And then Lineage list, one piece of feedback was to order items in downstream and upstream list. It would make it easier to skim through. Next slide, please. So this is what graph lineage looks like for us after the latest iteration. So as you can see, just level 1 nodes shown. The users are still free to open, unfold the nodes as they see fit. Next slide, please. So what's next? What we would like to see in our version of Amundsen is potentially column lineage. There is well, mainly for BigQuery, there are some improvements to be made. In terms of the UI and the table detail page, we would like to see the commonly joined with. So it's a bit of an improvement on the commonly used with that we've got. Also see recommended joins, that would be nice, and some section with data quality about a given table. So that would be it. Thanks very much for listening. And
thank you, Rob, Judy. Any questions for Rob or Judy? I see one. That's from Junda. Go ahead, Junda.
Hi, yeah, I want to ask a question. It seems like you made some, customization on the Amundsen. I want to know, do you feel it is hard for you to merge from the upstream, or you feel, very comfortable, merging from the latest upstream?
So we do fetch it from upstream. It's at times it's a little bit challenging. So the way we set up our GitHub repo is basically we forked from the public repo, and then we have 2 origins, and basically we have our own version which we continuously push, and every time and then we fetch the updates from upstream. It's much easier than it used to be, because at some point, I mean, a couple of months ago, we basically had this version that we forked a long time ago, and we never updated. So since we started using the fetching the updates from the upstream, it became the workflow became easier. I mean, that there are some merge conflicts that we have to resolve every time and then, but it's never caused us any serious issues. We've always been able to resolve everything.
Thank you.
Cool. We're almost at time, and I don't see any other questions coming in here. So I want to thank you, Rob and Judy, again for taking the time to present. It's super phenomenal the work you've done with Amundsen and King.